I'm Paul, this is Polymate 3D, and today we're going to be looking at WF81 Prototype 2 and going to be comparing it against the original. Let's get started. So from the data obtained in Prototype 1 in the last video, we can see a major gap between the performance of WF81 3D printed woofer and industry made woofer when it comes to sound pressure output and distortion. Sound pressure output is not an issue from 3D printing. This is simply a side effect of the small cost-effective magnets we are using. Tenacious 6, the next and final open source driver in the lineup, will be taking the first steps to addressing this and already is in the process of assembling the first prototype. Distortion, however, is not the case, and so I decided to examine Prototype 1 and look at what could be causing the issue. The first idea was the surround and the spider not having the same compliancy. They may be wanting to move at different amounts for a given weight applied, and this could be causing distortion. The top and the bottom of the cone could be fighting as they want to move at different rates. The other fault was the 3D printed cabinet itself. Typically, a bookshelf speaker is made of MDF or plywood with a high thickness compared to 3D printed ones, and has significantly more mass of material to move. It is possible this high distortion is from the cabinet deforming and emitting its own frequencies during use. After looking at both sides, I concluded that I believe the surround and spider were more to blame than the cabinet. However, once I have made the changes for Prototype 2, I would test in the 3D printed cabinet and outside to be able to get a better insight either way. This is where we are today and what this video will answer. So what changes did I make to WF81 and what were the reasons? The first step was going back to the prototype and looking at the suspension components. These are the surround and the spider. Using Fusion 360, I applied varying static loads in simulation to see what the results were, and concluded there was a decent variation between them, and alterations to both components were made to make them match as closely as possible. Other changes were to the voice coil, which has changed to be a lighter and thinner copper wire in the hope of increasing the SPL of WF81 to match what I wanted. This indeed was a success and produced 76 decibels at 1 watt at 1 meter in the WF81 4MN design. This meter crossover also had to change, but a simple change of value of this component was enough to continue to make this work. This is thanks to the FD51's flexibility. So next was to measure the Gale bookshelf speaker against Prototype 2 within the Endeavour cabinet again. 23.6% distortion is the number to beat. How much closer can we get to the Gale's 6.7%? The answer is 8.5% now as a peak, drastically undercutting Prototype 1 and having me class this version of WF81 as a success. My reason for this is because WF81 has to work harder to produce the same SPL, and so with the stronger motor, this distortion difference will no longer matter. What you can see in the distortion data, however, is spikes in the data with the Gale, and a smoother, consistent distortion in Endeavour. So what's going on here? Time to test the drivers on their own. To do this, I ran a test similar to what is done with the cone test platform. This time, the test was done at 2 volume levels, one volume significantly higher than the other, to see how distortion changes. The results were desirable, with WF81 averaging 1.86% to the Gale's 1.82% at lower volume levels. Increasing the volume and excursion of both drivers resulted in 2.71% distortion for WF81 and 3.14% for the Gale. This shows us that as the driver is pushed, WF81 3D printed driver is actually performing better than its industry rival. It also shows us that the driver is good, but the 3D printed cabinet needs some work. With these results in mind, however, I will be releasing WF81 to my Patreon supporters along with the Endeavour cabinet and crossover design. The design will be released to the public at the end of this month, along with kits for the wire, magnets, glue and TPU filament. So what is the next step? 3D printed cabinets need to be seriously investigated for their performance, as the increase in bass performance and the sound energy attempting to be tamed is also increasing. Many people use cement to fill a cavity in the wall to improve things, but I also have another idea on how to make use of 3D printers' capabilities to help this issue. Stay tuned as this will be coming up a little later, so get subscribed if you're not already and be first to find out what is the best way to create your own 3D printed speaker cabinets. Next up will actually be a resin printed cone, the first to not use FDM printing. I'm very interested in what MSLA printing can do from a cosmetic viewpoint, but the next video will be checking out how it performs as well, running back on the cone test platform. I hope you enjoyed the content and the insight into how I'm improving the possibilities of 3D printed speaker drivers. Please consider subscribing to the channel, as seeing you all following along drives me to continue my rate of design and thinking of innovative methods to improve the designs. If you have any pointers, questions or general feedback, message below or hit me up on Twitter and I'll get back to you. Most of all, thanks for watching, see you in the next one.